What if a machine could learn the same way you do? Not from some giant textbook or a massive data set, but just from pure experience, from trial and error. That's the incredible idea behind reinforcement learning, or RL for short. And today, we're going to break down how it all works and why it's totally changing the game for AI.
So to really get this, let's just start with something we all understand. I mean, how does any real learning actually happen? Think about it. How do you teach a dog to fetch? Or remember when you were a kid learning to ride a bike? What's really going on there? It all comes down to trial and error, right? You try something, you see what happens, and you adjust. If you do the right thing, maybe you get a treat. If you fall off the bike, well, you learn what not to do next time. This super simple, intuitive concept, that's the absolute heart of reinforcement learning.
And you know, this isn't just some casual saying. It's actually a scientific principle. The whole story of reinforcement learning actually has these deep roots in psychology, believe it or not, specifically in how animals learn. Researchers were trying to figure out the basic rules that shape behavior based on consequences. And this idea has a name. Way back in the early 1900s, a psychologist named Edward Thorndike called it the law of effect. It's a powerful idea, but it's really simple. Actions that lead to good things tend to be repeated. Actions that lead to bad things, you avoid them. And that is the exact same logic we use to teach an AI.
Okay, so how do we take that principle and actually apply it to a machine? Let's get out of the abstract and look at something real. We're going to follow a robot as it literally takes its first steps, learning a brand new skill completely from scratch.
So this is our learner, a Franca Emica Panda robot arm. It's got a camera for its eyes and a little gripper for its hand, and its entire goal in life, the whole reason it exists, is to figure out how to push that little puck to the edge of the table. That's it. But here's the thing, it starts out knowing absolutely nothing. No instructions. So where does it even begin?
Well, before a robot can learn anything at all, we have to define its world. We've got to set up the rules of the game. And it turns out pretty much every reinforcement learning problem, whether it's a simple robot arm or some world-changing AI, is built on the exact same 4 key ideas. First up, you have the agent. This is our learner, the one making the decisions. In our case, it's the software controller. You can think of it as the brain of the robot arm that has to figure out what to do.
Now, the agent exists inside of an environment. This is literally everything it can interact with. For our little robot, the environment is the physical table, the puck itself, and all the visual information it's getting from its camera.
And inside that environment, our agent can perform actions. These are all the possible moves it's allowed to make. For our robot, the actions are pretty straightforward. It can choose to move its gripper up, down, left, or right.
And here we go. This is the most important piece of the entire puzzle, the reward. This is the feedback. It's just a number that the environment sends back to the agent after it takes an action. Did that move get it closer to its goal? Positive number. Did it do something useless? 0. The agent's only objective, its entire reason for being, is to take actions that get it the highest total reward possible over time. That's it. This brings us to one of the most powerful and kinda audacious ideas in all of AI. It's called the reward hypothesis, and it basically says that any goal, and I mean anything you can possibly imagine, can be framed as just trying to maximize some simple numerical score. Winning a game of chess, pushing a puck, managing a city's traffic, it all just boils down to getting the highest score. So we have the rules. The robot can start learning through trial and error. But there's a problem. Doing all this learning in the real world is incredibly slow. It's expensive, and, you could actually break the robot if it makes a really bad move. The obvious answer is to just train it in a simulation first. But that creates its own huge problem. It's called the sim-to-real gap, and it's one of the biggest headaches in robotics. See, a simulation is this perfect, clean digital world where physics works exactly as programmed.
The real world, though, it's messy. It's got weird, unpredictable friction, the lighting is always changing, there are tiny imperfections everywhere. So a perfect plan that's learned in a simulation, it almost always fails, and often spectacularly, the second you try it in reality.
So that puts you in a real bind, right? If the simulation is too perfect to be useful, but the real world is too slow and risky to learn in from scratch, what do? It feels like you're stuck. But this is where the researchers behind our little robot arm got really, really clever.
Instead of using the simulation to find the perfect solution to the problem, they used it to learn something much simpler: how to just explore safely and efficiently. So first, inside their fast simulation, they trained a whole bunch of different exploration strategies. Think of them as different ways of just trying things out. Then, they took those safe exploration strategies and let the real robot use them to gather data in the messy real world. And finally, they took all of that valuable real-world data and fed it to a final AI agent, which could then figure out the best way to solve the actual task.
And that's really the key here. This whole framework of an agent, an environment, and a reward, it's not just some neat trick for robots. It is a powerful, general-purpose recipe for solving a mind-boggling range of complex problems.
Think about it. Anytime you have a system that needs to make a series of decisions to achieve a goal in a complicated, changing environment, this exact same idea of learning from interaction can be put to work.
The applications are just staggering. I mean, this goes all the way back to the 1950s, when a program learned to play checkers so well that its own creator described it as tricky but beatable. But today, this same core idea is used to dispatch elevators and skyscrapers to cut down your wait time, to manage bandwidth in cell networks so your calls don't get dropped, to schedule incredibly complex jobs in factories, and yeah, even to master insanely strategic games like StarCraft 2 at a level that no human could ever hope to match.
Ultimately, reinforcement learning is this fundamental shift in how we build intelligent systems. We're moving away from painstakingly hand-coding instructions for a machine. Instead, we just define a goal through a reward, and then we let them figure out the best way to get there, all on their own, through their own experience. And that leaves us with a really fascinating question. If these systems can truly learn from their own mistakes and successes, what will they learn to do next?